Welcome to 17th lecture. In this lecture, we will study a very famous theorem regarding mean and standard deviation of either a sample or the population. It works on both. It works on both sample and the population. And the theorem is that for any given number k, that can be a real number, can be an integer, it can be 1 2 or it can be 1.5 1.2, but or 2.5 2.3, it should be greater than 1 and can be any real number, and a set of n measurements. If it is small and this means this is a sample, and if it is capital and this means it's a population. The algorithm, the theorem works on both the sample and the population. So given a number k that is greater than or equal to 1 and n measurements, at least 1 minus 1 upon k squared of the measurements lie within k standard deviation of their mean. This means if this is the distribution of the data and this is the mean mu, and this envelope describes the distribution of the data, then for any k, if we go below mu and reach to a point mu minus k sigma, where sigma is the standard deviation, and if we move to the right from the mu and reach to a point mu plus k sigma, so the area that is under this curve, there are at least in this range we have at least this much, this number of observations or data points or measurements, 1 minus 1 over k squared. So if we set k is equal to 1, these limits are mu minus lambda, so mu minus sigma and mu plus sigma, and of course this width would be smaller. But if we set k is equal to 2, that would be mu minus 2 sigma and mu plus 2 sigma. In that case, the width would be larger and there will be more data points or more number of measurements in this range. But in any case, no matter what is the value of k, if it is greater than 1, this algorithm is proven to be correct. This theorem is proven to be correct. We have at least 1 minus 1 over k squared observations in this range. Right, so in order to understand this theorem better, let's solve this example. We are given this range of numbers 5 7 1 to 4. It's a small sample of n is equal to 5, and in previous lectures we have computed its mean and the standard deviation. Right now we have used for this sample we have used this x bar to represent mean instead of mu. Why? Because it's a sample, and for sample we use x bar to represent mean, and we have used s to represent standard deviation, and we haven't used sigma. Why? Because we use s for sample and sigma for population. So right, therefore we have used the correct terminology, x bar and s, because it's a sample. So now let's verify Chebychev's theorem on it. Let's suppose we have k is equal to 1 first. Let's check it for k is equal to 1. If you put k is equal to 1, it is 1 minus 1 over 1, it's a 0. This means at least we should have 0 measurements in x bar minus at s and x bar plus s. Why s? Because k is 1, so 1 times s is a 1 s. 1 times s is s. So we have at least 0 observations or 0 measurements in this range. X minus s is, we have got this data, we have computed x bar and s is 3.8 and 2.39. So 3.8 minus 2.39 is 1.41. So this gives us this lower limit, and if we add these two, this gives us this upper limit. So we should have at least have 0 measurements. According to the theorem, we should have at least 0 measurements within this range, but actually we have more than 0. We have 3 measurements. So for k is equal to 1, the theorem is working fine. Let's check it for k is equal to 2. Let's put k is equal to 2. 1 minus 1 over k squared. 2 squared is 4. So this 1 minus 1 over 4 is 3.4. So 3.4 of n, 3.4 of n, because n is 5, we have 5 measurements. This comes out to be 3.7. So we have at least 3.7 measurements in this range, x minus 2, x bar minus 2s. This is k, 2, k is 2, x bar and x bar plus 2s. Let's find out what these limits are. X bar minus 2s is minus 0.98, x bar plus 2s is 8.58. So within these two limits, this range defined by minus 0.98 and plus 8.58, we should have at least 3.7 observations. But let's see how many observations we actually have, how many measurements we actually have. 1, 2, 3, 4, 5. We have all 5 measurements in this range. So we should have at least 3.7, but we actually have 5. So this means we have verified Chebychev's theorem for this example. Right, let's probe into this theorem a bit more by looking at example number 2. This is lesson plan assessment scores. The teachers are given an assignment to prepare a lesson plan before they deliver their lecture in classroom, and this is the assessment of those lesson plans, that whether the lesson plans prepared by students were effectively conveyed in the class or not. They were assessed on a scale between 0 and 34. So the maximum number we see here is 31.9, and the minimum number is maybe this is 10.2. So these are 25 lesson plans randomly selected from teachers in a university to see whether they are able to communicate their lesson plans or deliver their lessons according to the plan or not. So I have plotted a dot plot for this. I have plotted a dot plot for this data. It's a dot plot having all these 25 numbers. The assessment scores earned by 25 lesson plans from different teachers. So this is the dot plot, and you can use the techniques, the formulas we have studied in the last couple of lectures for mean and variance, or mean and standard deviation of sample, of course, having n minus 1 denominator. So it comes out to be 5.5 and mean is 21.6. So this standard deviation was computed using n minus 1 in denominator because it's a sample of 25 measurements. So now we are going to do is we are going to check for k is equal to 1. We are going to check whether the Chebychev's theorem is verified for this example or not. So this is what we are going to verify. For k is equal to 1, the range is x bar minus k is 1, x bar minus s. X bar minus s is 21.6 minus 5.5. This comes out to be 16.1. And the upper limit is x bar plus s, 21.6 plus 5.5, it's 27.1. So there must be at least, put k is equal to 1 here, 1 minus 1, 1 over 1 is a 1, and 1 minus 1 is a 0, 0 times 25. We should have at least 0 measurement in this range, but we actually have 16, a lot more than 0. Right, so this theorem is verified for k is equal to 1. Let's check it for k is equal to 2. Putting k is equal to 2, this is 21.6 minus 2 times 5.5, I mean 11, 21.6 minus 11, this is 10.6, and the upper limit is 21.6 plus 11, plus 2, 21.6 plus 2 minus 232.4, 32.6, I guess this is a small mistake here. 5.5 to 5.5 is 11, maybe 32.6, right? So we should have k, putting k is equal to 2 is 1 over 4, so 1 minus 1 over 4 is 3 by 4 times 25 gives us 18.75. So we should have approximately 19 measurements in this range, which range from 10.6 to 32.4. In this range we should have at least 19 measurements, but we actually have 24 measurements. You can verify it from this, from here, from 10.6 to 32.4. from 10.6. From 10.6. Maybe this is 10.6 to 32.4. So we have 24 measurements. Only one measurement is out of this range. So we have 24 measurements. Actually, we have 24 measurements, a lot more than 19. This means that Chebychev's theorem is verified even for k is equal to 2. And let's check it for k is equal to 3. And putting k is equal to 3 and putting x bar and s, the values of x bar and s taken from this page, these two values, the range comes out to be 5.1 to 38.1. And in this range, we should have at least, putting k is equal to 3 in this equation, the answer is 22.2. We should have at least 22 observations, 22 measurements in this range, but we actually have all 25 in this range. All 25 measurements in this range. So the Chebychev's theorem is verified even for k is equal to 3, and it will be verified for all higher values of k too. You can try it at home for k is equal to 1.5. You can try it for that, maybe for 1.8. You can try it for a value between 2 and 3, for many values between 2 and 3. Maybe you want to try it for 2.4. Maybe you want to try it for 2.7. And you'll see Chebychev's theorem will be verified for all chosen values of k, but the values should be greater than 1. That you should keep in mind. K should be greater than 1. So Chebychev's theorem is verified even for this example, and it will be verified. You can choose any example from the book, or you can imagine any set of numbers, or you can imagine any sample of numbers, and it will be verified. And and if you check it for different values of k, you will verify for all values of k, provided k is greater than 1 or greater than or equal to 1. So in the next lecture, we are going to do the same thing. We'll run a Python simulation to verify Chebychev's theorem. We will select a sample of randomly generated numbers. These numbers may be 10, they may be 100, it will depend on the user. They may be 10, 20, 30 numbers, and they will be randomly selected from a given range of integers. So maybe when you run the simulation, you will be asked to enter how many numbers you want to enter. Maybe you say I want to have a sample of 10 integers. Then you will be asked the lower limit and the upper limit of integers. Maybe you say I want them to be from 0 to 50. The number should be from 0 to 50. And then the simulation, as the simulation will run, it will give you k, that for k is equal to 1, you should have how many number of measurements in this range. This is the range. How many number of measurements you should have in this range, and how many number of measurements are actually present in your data. And you'll see that the actual number of measurements will always be the number of measurements suggested by the Chebychev's theorem. So that will be an interesting simulation. We'll do that in our next lecture, P&S18. Right, that's all for this lecture. Thank you for being with me.